In this video, I'll discuss solving trig equations. You'll see that solving trig equations involves blending your algebraic skills with the geometric relationships that you've been studying. We'll start with a simple example. Here we're asked to determine all solutions to these two equations. First, cosine theta equals 1/2. To determine all solutions, I'll draw a unit circle. And I'll draw a vertical line approximately at x equals 1/2. As you can see, that vertical line intersects my unit circle in two places, helping me visualize the two types of solutions. The first is theta equals pi over 3, and the second is theta equals 5 pi over 3. Now, to describe all solutions, I'll just indicate that any angle that is coterminal to pi over 3 will solve the equation by adding multiples of 2 pi, and any angle that is coterminal to 5 pi over 3 will also solve the equation. And there's my complete solution set. And this is where k is an integer. For the second one, sine squared equals 1/2, I'll start by taking the square root of both sides. This will give me sine theta is equal to plus or minus the square root of 1/2. The square root of 1/2, of course, is also known as root 2 over 2. So here I would like to know where the sine function achieves a value of plus or minus root 2 over 2. For this, I'll draw a horizontal line, approximately 0.707, and another horizontal line at negative 0.707. And this helps me visualize 4 different types of solutions. And they are pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now, when it's time to describe the complete solution set, I have a couple options. One, I can list pi over 4 and all angles that are coterminal to it. 3 pi over 4 and all angles that are coterminal to it. 5 pi over 4 and all angles that are coterminal. And lastly, 7 pi over 4 and all angles that are coterminal. Or I could notice the geometry of my solutions. Pi over 4 is perpendicular to 3 pi over 4, which is perpendicular to 5 pi over 4 and perpendicular to 7 pi over 4. That is to say that all of these angles that solve the equation are exactly pi over 2 apart. And thus, I can list my solutions this way. In this example, I'll see how I can adjust the work that I did in the last example when I have a change in frequency. So I'll start off by drawing a unit circle and visualizing when the x coordinate is equal to 1/2. I can see that the x coordinate achieves a ratio of 1/2 at pi over 3, and then over here at 5 pi over 3. So I can start off this problem by saying 2 theta is either equal to pi over 3 or 2 theta is equal to 5 pi over 3, leading to 2 solutions for theta, pi over 6 and 5 pi over 6. But it is important to note that these are not the only 2 solutions for theta. And that's because I have a frequency of 2. So if you picture the graph of cosine 2 theta on the requested interval, of course, cosine will complete one cycle in pi radians because it has a frequency of 2, and then it'll complete a second cycle by the end of 2 pi radians. And thus we can see when I draw a horizontal line at x equals 1/2 that there's 4 solutions on this interval, and I've only found 2 of them. The 2 that I found are within the first cycle, and I can find the other 2 simply by adding the period to each of the first 2 solutions. So if I take this solution of pi over 6 and add pi, I'll get 7 pi over 6. That's my third solution. And then if I take 5 pi over 6 and add pi, I'll get 11 pi over 6. And that's my fourth and final solution on the interval from 0 to 2 pi. In letter B, we have a similar situation, except it's sine of 3 theta, so I'll be expecting 3 times as many solutions on the interval from 0 to 2 pi. I'll start by drawing a horizontal line at root 2 over 2, so it's about 0.7, and that intersects at an angle of pi over 4 and an angle of 3 pi over 4. And thus I could say that 3 theta is either equal to pi over 4, or 3 theta is equal to 3 pi over 4, leading to 2 solutions once again, pi over 12, or I'll just call it 3 pi over 12 for now. I can reduce it later. All right, and then here's a picture of that sinusoid, which is also really helpful. So this is sine of 3 theta. So it does 3 cycles on the interval from 0 to 2 pi. And that is to say that one period, the length of one period, is 2 pi over 3. So this is 2 pi over 3. And thus, to generate all of the solutions on the interval from 0 to 2 pi, I can start with pi over 12 and 3 pi over 12. And I can keep adding this period, which in twelfths is 8 pi over 12, to each of these 2 solutions. So if I add 8 twelfths to 1 twelfth, I get 9 twelfths pi. If I add 8 twelfths to 3 twelfths, I get 11 twelfths pi. And I'll repeat this once more, adding 8 pi over 12 to each of the new solutions that I generated to give me 17 pi over 12 and 19 pi over 12. And these are the 6 solutions that you see when you draw a horizontal line at 0.707, or about root 2 over 2 on the interval from 0 to 2 pi. In this example, you'll see that sometimes you might need to rely on a graphing calculator because you might have a sine or a cosine ratio that is unfamiliar from your study of the unit circle. So here we see we want to solve for theta. Theta this time is in degrees between 0 and 360. And we're told that cosine of theta is equal to negative 0.134. So I can still include a sketch. That can still be helpful. I want to know about an x coordinate, so I can draw a vertical line at x equals negative 0.134, something like this. That can be helpful. But ultimately, I'm going to need my calculator to get this started. I need to, on my calculator, in degree mode, evaluate cosine inverse of negative 0.134. And this will give you 98 degrees, which, of course, will be one of the solutions. The second solution is simply going to use the symmetry of the unit circle here, and it's exactly equal to 360 minus the theta that I found. This is always going to be true for cosine. So 360 minus 98 is going to give me 262 degrees. And these are my 2 solutions on the interval 0 to 360. 262. Okay. When I work out a similar problem for sine, of course, there's a slight difference. I want to know where sine is equal to 7/8, so I can draw a vertical line here about 7/8 up close to the top. I'm still going to need my calculator to get things started. I evaluate inverse sine of 7/8, and that gives me 61 degrees. Okay, so one of the solutions here is 61 degrees. Notice that the other cannot be found by doing 360 minus 61 because sine has a different symmetry on the circle. I have to do 180 minus 61 degrees to get the other solution. That's 119 degrees. And these are my 2 solutions on the interval from 0 to 360. In this example, we'll have to use some of our algebra skills in addition to our trigonometry skills. I'm going to start out by substituting q for sine and rewriting this quadratic in standard form, 2q squared minus q minus 3 equal to 0. And now I'm going to try to factor the quadratic that I have here. If you're ever doing one of these problems and you can't factor, you can always just use the quadratic formula. I think this one will factor without too much trouble, -3 and +1. And this leads to two solutions for q. Q could either be equal to 3/2, or q could be equal to -1. Okay, and now I'll substitute sine theta back in for q. Sine theta could be equal to 3/2, or sine theta could be equal to -1. This first equation is, of course, a dead end because, well, sine theta has a range from -1 to +1. It never achieves a height of 1.5. But the second one has a solution. So y is equal to -1. I can see right here that happens at 3π/2. And that is my lone solution on the interval from 0 to 2π. Here's a similar example, except it uses tangent. And this one, you might need a calculator for a portion of it. I'll start by substituting q for tangent of theta. And then again, I will factor. I get q minus 7, q minus 1. So q is either equal to 7 or 1. And that is to say that tan of theta is either equal to 7 or tan of theta is equal to 1. Now, tan of theta equal to 7, this is something I'd need a calculator for. I would want to figure out when theta was equal to arctan of 7. And working in degrees, that is at 82 degrees about. All right, and then the second one, I guess since I'm using a calculator, I might as well continue, but you could figure out that the tangent of 1 occurs at 45 degrees. Okay, so I get two different solutions, and I'm asked for all solutions of the equation. It's important to note here that the period for tangent is 180 degrees. So if there's a solution at 45 degrees, then there's another solution 180 degrees later. And if there's a solution at 82 degrees, then there are more solutions, of course, every 180 degrees after that. In our next example, we'll need to continue using some algebraic skills in order to solve, but you'll notice here that if I substitute, say, q in for sine, I'll get 1 equals 3q squared plus 5 cosine, and that doesn't really get me anywhere. What I need to do is something a little more clever. What I can do is recognize that this equation involves both sine and cosine. And here we have a sine squared. You might remember from our study of the unit circle that sine squared plus cosine squared equals 1 for every value of theta that you can imagine. And that is to say that 1 minus sine squared is equal to cosine squared, or 1 minus cosine squared is equal to sine squared. And to solve this problem, I'm going to substitute that variant of the Pythagorean identity in, and this gives me an equation that's entirely in terms of cosine. So I'll do a little simplifying. This will be 3 minus 3 cosine squared plus 5 cosine. Okay, so if I write this quadratic all on the left-hand side, I'll get 3 cosine squared theta minus 5 cosine theta plus 1 minus 3 would be minus 2 equals 0. So now I have the equation 3q squared minus 5q minus 2 equals 0, where q is representing cosine of theta. And again, I can try to factor this. If you're ever unsuccessful in factoring, you can always use the quadratic formula. You can see q is going to be equal to the opposite of -5. So that's 5 plus or minus the square root. And then the b squared minus 4ac would give you -5 squared minus 4 times 3 times negative 2. And that's going to be 25 minus negative 24. So that'll equal 49. So I've got a 49 under the radical here. And this is all over 2a, so it's over 6. And that is to say that q is going to be equal to 5 plus 7 over 6. That's 2. Or q is equal to 5 minus 7 over 6. That is negative 1/3. And remember, of course, that q is equal to cosine of theta here. So either cosine theta is equal to 2 or cosine of theta is equal to 1/3. Okay, I'm not quite done just yet. I now need to figure out the solution to those two equations. Cosine of theta equals 2 is a dead end because the x-coordinate on the unit circle never reaches a ratio of 2. Or you could think of it as the adjacent to the hypotenuse ratio couldn't be 2 because that would mean the adjacent was larger than the hypotenuse. But cosine theta does equal 1/3. I can find those solutions and visualize them as such. I need a calculator to get this started. So I have to do theta is equal to cosine inverse of 1/3 to get my first quadrant angle. And that's about 70.5. I'm just going to call it 71 degrees. That's this angle up here. All right. I want all angles between 0 and 360. So I also have to find this angle down here. And that can be found by doing 360 minus theta. 360 minus 71 gives me 289 degrees. And those are the two solutions to this problem, 71 and 289. Our last example here is probably the most challenging from an algebraic standpoint, but with a really good knowledge of a unit circle, you probably could just pick off a solution to this equation right away. We're asked, where on the interval from 0 to 2 pi is the sum of the sine and cosine equal to root 2? So just kind of picturing your unit circle, or with a really strong knowledge of your unit circle, you know that at 45 degrees, or at pi over 4, both the x and the y coordinate are root 2 over 2. And obviously, if we add those together, we get root 2. The question is, are there any other places where this is true? So the algebra that we'll use here is a little bit involved. I'll show you what you should do. First thing that you should do is subtract a cosine from both sides. So rewriting the equation this way. Now what I'd like to do is have an equation that's just in terms of sine or just in terms of cosine. I can get there by squaring both sides. So just to show you how that's going to work out. On the left, I'll get sine squared of theta. And on the right, I'll get the binomial. So just to be clear here, when I square the left-hand side, this is very important that you actually multiply it by itself. So you get root 2 minus cosine theta times root 2 minus cosine theta, right? Don't just square the root 2 and square the cosine. Root 2 times root 2 is 2, and then root 2 times negative cosine theta doubled would be negative 2 root 2 cosine theta, and lastly, negative cosine times negative cosine would give you cosine squared. Okay, so this looks a little messy here, but what you'll notice again is I get a sine squared here, and everything on the right-hand side is in terms of cosine. So it's to my benefit to rewrite sine squared using that Pythagorean identity as 1 minus cosine squared. And that gives me this equation. Right, this is headed in the right direction. Okay, and now if I group all the terms on the same side of the equation, I'll just group everything on the right here. I'll have 2 cosine squareds, the negative on the left plus the positive on the right. And then I'll have minus 2 root 2 cosine theta. And then I'll have plus 1. And all that equals 0. Okay, so I'll have the quadratic form 0 equals 2q squared minus 2 root 2q plus 1. And this is what I'll need to factor and solve. This actually factors very nicely. It's just a little non-standard. You can do root 2q minus 1 times itself. It's a perfect square trinomial. And you might notice that because the square root of the leading term doubled is the middle term. And so q is equal to 1 over the square root of 2. And that is to say that cosine of theta is equal to 1 over the square root of 2, or root 2 over 2. Okay, and we know two angles on the interval from 0 to 2 pi where this is true. And the first, of course, is pi over 4. We had that one, right? The other spot where cosine of theta is equal to root 2 over 2 is down here at 7 pi over 4, right? But the thing about 7 pi over 4 is we'll see it doesn't solve our equation, because if I were to add sine and cosine at 7 pi over 4, they would cancel each other out because they have opposite signs. They would not add to root 2 over 2. And what that tells me is this 7 pi over 4 solution is extraneous. So you'll note back in my second step, I had to use that algebraic technique of squaring both sides. And that was really necessary so that I could get sine squared here, which could substitute 1 minus cosine squared, so everything was in terms of cosine. It was really a necessary step, but it was also a step where I created an extraneous solution. And so it's important to know that if you utilize this technique of squaring both sides, you absolutely must check your answers at the end and see if they are all valid. I hope you enjoyed the video and that you're starting to see that solving trig equations involves a nice blend of algebraic skills and geometric understandings about sine and cosine ratios.